Graduate.
Sorry.
Okay, I'm going to back up again.
Yeah, thank you.
Okay,
Sorry
so our
about that.
guest speaker tonight is Dr. Keren Sharon. She is an associate professor and an undergraduate advisor at the University of Michigan. University work kind of partial. She earned her Bachelor of Science and PhD from Tel Aviv University in Israel. Keren is a Kavli postdoctoral fellow at Kavli Institute of Cosmological Physics at the University of Chicago and University of Michigan President's postdoctoral fellow. Keren Sharon's research centers on strong gravitational lensing, a phenomenon in which the gravitational field of a massive structure bends light from objects behind it, allowing it to serve as a natural telescope. Her group studies the massive structures themselves, and they also use the exceptional magnification provided by these lensing structures to probe the physical properties of background galaxies. They can examine distant galaxies with unprecedented resolution and detail. Of note is Keren's group's discovery of the largest multiplicity high redshift lens quasar in 2013. And they were awarded 7 orbits of the Hubble Space Telescope in 2014 to observe this unique system. Keren uses lenses and mirrors a bit larger than we have available in our club. And tonight she is here to talk to us about what she can do with them. So with that, please welcome Dr. Keren Sharon.
Update that list that we got way more than 7 orbits on HST since then. No, it's impossible to keep things updated these days. I'm not going to unmute myself. And I got it that we're being recorded. All right. Hi. I hope people at home can hear me. If you're at home, can you please mute yourself so that we don't hear you chewing your dinner, for example.
Oh, rats.
All right. Thanks for the lovely introduction. I'm really happy to be here, and I'm even super excited to be here in person and talk to you in person. I think the first time I was contacted with an invitation was, I don't know, 1.5 years or 2 years ago or something, 1.5 years ago. And I was like, well, you know what, maybe can we plan on doing this after all this? And maybe we can be in person. So one of you probably said, oh yes, what about October 15th? I was like, yeah, sure, we'll be over all this by then. But yeah, so I'm extremely happy to be here. Thanks for the invitation. Thanks for the opportunity to give back. I actually went to one of the Astronomy at the Beach events and looked through probably some of your telescopes. So I really appreciate that opportunity. Just that. Okay, here. So my name is Keren Sharon. I'm an astronomy professor at U of M. And I always like to say that for my job, I look at pretty pictures of space and try to figure out how the universe works. And this is pretty much what I do. And you'll see today lots and lots and lots of pretty pictures. Not a lot of words, and maybe one equation, maybe. And my favorite astronomical object, surprisingly, is the moon. I love the moon. I love looking at it through a telescope, especially since I can, see all those craters and see it in 3 dimensions. And my brain kind of sees the phases of the moon, and I can see it in my mind, where our place is within that moon-Earth system, and how like the moon moves around the Earth and where the sun is. And it's just kind of mind-blowing that we're little us are able to understand all that. Even though for my job, I study the universe as a whole and things that are the farthest things out there that we can see with telescopes. But still, the moon is my favorite. I love telescopes, and my favorite telescope is the Hubble Space Telescope, shown here. It's my favorite. It's taking beautiful pictures for us. As As you probably know, it's not the biggest telescope out there. It's only 2.4 meters, and the size of the whole observatory is about the size of a school bus. So it's not enormous or way bigger telescopes on Earth. But because it's above the atmosphere, it allows us to not have to worry about the pesky atmosphere and the seeing and blurriness and all that. So it was designed to give us beautiful pictures like this. This is actually that's a very recent picture of Jupiter. There's this wonderful program that takes a current picture of all the planets every year, just to keep studying them with Hubble for the duration of Hubble's lifetime, which is great. I don't really care about planets, so it's taking pictures like this. This is a picture that was taken as part of Hubble's 25th anniversary. And you can see here star clusters and giant molecular cloud, star forming region. Is this in your way? Are you okay? And so this is within our galaxy. All the stars here, this is a star cluster, so it's in our galaxy. You probably have seen enough to appreciate what sizes we're talking about. But also things that are outside of our own galaxy, like this beautiful tadpole galaxy, where this was released in 2002. And I actually remember, when that image dropped. It was the ACS camera on HSD was just commissioned, and that was one of those images, press release images that they released for the community, for people to kind of, be in awe. And yeah, there's like lots of structure, and you can see the spiral arms, and you can see the dust, and you can see the gas, and you can see this, whatever it is that's happening here. It's like pulling all those stars away from this galaxy. But I was a grad student. I remember looking at this picture, and I opened it on my computer, and I opened the largest resolution that was available. And I was mesmerized by this object, but also started looking at the background. And I realized that each one of those specks of light in the background is its own galaxy. And as far as you look, there's like galaxies all the way out. It's pretty amazing. Kind of like looking at this and realizing that just kind of casually in the background of that galaxy, there's millions and millions and millions of galaxies. So this image probably has like 2,000 of them. And I kind of wondered to myself, what would happen if you just looked, are there galaxies all the way out? Is it turtles all the way down? Can you just like, no matter where you look, are you going to see galaxies everywhere? And obviously I wasn't the first one to think about this. You just need to the telescope, point Hubble at somewhere like really for a very long time to see very, very deeply, right? But this is not something that just one person can do with Hubble. Maybe you can do this with your backyard telescope, point it at one piece of the sky and observe forever, or take a picture for a very long time. But like, I can't do this with Hubble. You need the whole community to be behind an endeavor like this. And it turns out that if you are the director of the Hubble Space Telescope, then you can do that. You can take the telescope and point it for a big chunk of time at whatever you want. And the director of the Hubble Space Telescope decided that this is something that's worth doing, and pointed the telescope at a blank piece of sky, obviously with a lot of input from the community and advising, and people told them what's useful for the telescope to do with this amount of time. And you probably know where I'm going with this. This is going to be the Hubble Deep Field. So Hubble pointed at, they chose a blank piece of sky with no stars in the foreground, no known nebulae or background galaxies or anything like that. And you can all identify this constellation, right? So it's up there in the north, meaning that Hubble, as it spins around the Earth, it can observe this almost continuously, only stopping for the time that it takes the data to read out and download. So they pointed at this piece of sky that has absolutely nothing in it. And then they opened the picture, they saw this, lots and lots and lots of galaxies in this tiny little piece of sky. This picture has probably 2,000 or 2 or 3,000 galaxies in it. I forget the actual number. And it's amazing in its richness. And it's something that you really need a lot of observing time to reach. This was taken over a whole 10 days of Hubble time. And it's a tiny field of view. Does anyone know how big this field of view is? So if you take your fingers and make the smallest possible pinhole that you can, still see something, and then put it at arm's length, that's the field of view of Hubble. Very, very small. And there's all this richness of galaxies in it. Pretty amazing. But, and there's lots of research that has been enabled by this type of image and type of data, which went publicly available immediately. But we're not going to stop there, right? We're going to try to observe it even deeper and deeper. So as Hubble advanced with new technology, with new cameras, they kept observing this piece of sky and similarly other pieces of sky with new cameras and obtained the ultra deep field and started really peering into the deep universe and seeing galaxies that are really far away, meaning that the light that we're seeing from those galaxies is ancient because light travels at the speed of light. So if you're seeing something that is 10 million light years away, then the light started leaving that galaxy 10 million years ago, or 10 billion light years away, then you're seeing the universe as it was when it was an infant. So here's an example of a really far away galaxy that was detected in the Hubble Ultra Deep Field. You can see it here. When we're able to add infrared cameras, we can see even farther into the universe because of the stretching of light due to cosmological redshifting. So obviously not going to stop even there, adding more and more data, peering deeper and deeper and deeper into space with the extreme deep field. Astronomers don't have very good ultra to extreme. The naming system could be improved upon. So this is what the extreme deep field looks like, and identifying even farther galaxies and data like that. This is to show you how, like, all those the different data that went into combining all that data into one very deep image. So as we move along the years, our technology, our telescopes are better, bigger glass, going out to space, better cameras, better detectors, going out to infrared, and so on. We're peering deeper into space. And this is the Hubble Ultra Deep Field about 10 years ago, going all the way to 500 million years after the Big Bang. And in the future, we're hoping to have bigger telescopes, even in space and on the ground. I used to have a slide that said that James Webb will be launched in 2018. This actually had that, and I just changed it. I kept changing it every year because it keeps being pushed. The launch date kept being pushed and pushed and pushed. And now hopefully this is going to happen in 2 months and 3 days, not that we're counting, December 18th, 2021. So keep an eye out for that. It actually was recently packaged and put in a crate and folded up, packaged, put in a crate. I thought this was mesmerizing. I watched it like 7 times. Like I have close colleagues who that's their career, like working on James Webb. So it's extremely exciting and a little bit anxiety driving. So this is really recently, they put it on a ship, and the ship actually made its way. And the next thing that's going to happen is that it will be launched I'll just finish this little time lapse. All right, so the ship made it safely, no pirates hacked it along the way. That was a real concern, I hear, at NASA, that pirates will. If I were a pirate and I kidnapped JWST, I would probably ask for a lot of telescope time in order to release it back. Give me all the HST time and I'll give you your telescope back. Right, so next thing it's gonna do is it's gonna leave Earth and make its way to the L2 point, the Lagrange point. And then after they folded it up, they're gonna have to unfold it and open up all the shields and the mirrors. And I just think it's so cool. It's such a wonderful technological, and I don't know, I'm just like, I'm excited. Can't wait for this telescope to come, because I think once JW stays out there, we will really be able to go all the way, very deeper than we ever could, and look at galaxies that we never were able to, even with the gravitational lensing that I'm going to talk to you about. But taking JWST and adding gravitational lensing to it is going to be even more amazing. So I think it will give us a new look at known object, even in a way that I don't know, it's going to be amazing. Keep an eye out. 2 months, 3 days. What?
You have the owls comment too, right?
I will when we get close. Right, but so not just that. So on the ground as well, we're going to have new telescopes that are currently being built in order to do basically the same thing. Look deeper, bigger glass, higher resolution, more light collecting power, to be able to do two things. One, look farther away, and two, get better detail. So you get more photons, you can take better spectra, you can understand what the chemical composition is of galaxies, and you can resolve them into, instead of just looking at one little blob, you can look inside the galaxy that's really far away and understand how it works and what it looks like. And like, you know, give me a bigger telescope, I'll be happy, right? Bigger glass. The University of Michigan actually recently joined this EELT, European Extremely Large Telescope endeavor. That's 2030-ish, but we will have the university is going to have some time on this telescope as well. So I just wanted to pop it up there. Right, so this is great, but we don't want to wait, right? We don't want to wait until the EELT. We don't want to wait until JWST, even though the wait has been shortened. But there is something you can do while you're waiting for the big next telescopes, and that's to use nature's telescope and stick a magnifying glass between your currently available telescope and the rest of the universe. So this magnifying glass comes in the form of a gravitational lens. Now we can't just put the lens anywhere we want, so we need to rely on a little bit of luck. So we have to look in the direction where the telescope is already there, but I'll show you how we do that. So just like a regular lens is bending light and magnifies and distorts and collects light like in our telescope, a gravitational lens is doing the same thing, or basically space-time is doing a very similar thing. In the presence of mass, any mass, even you and me or your pop bottle, space-time bends a little bit or a lot, depending on the amount of mass. And light is forced to move on, we call it null geodesics, or straight lines on this curved path. So if this comes right out of Einstein's general relativity. So if there's a background source here at point A over here, the light is leaving that point in this direction. Instead of going that way, it bends around this massive object and hits Earth. And from the point of view of Earth, we're seeing the light as if it's coming from this position B instead of A. So the object's position gets moved a little bit in the sky. It's a tiny, tiny amount, but we can detect that. And just like regular lenses, it sometimes gets distorted and the amount of light gets magnified. So it's great. Einstein didn't actually think this would be observable, but turns out that it is, and I wouldn't have a job otherwise. Or maybe I would like work on planets, I don't know, because astronomy is amazing. Right, and very, very much like optical lenses or optical surfaces that reflect or break light, gravity does that as well. So here are some examples. All right, we have like I'll show you more of that in a minute. So reflecting things, we look at those reflecting surfaces and we kind of know that things look distorted, right? We know that, that the room is distorted. How do you know that this is a curved or not a regular flat mirror?
Be parallel.
Yeah, lines that should be parallel aren't. How about this one? The horizon is not flat, right? How about the cloud? Do you know if the cloud is distorted or not? Clouds come in all shapes and sizes, right? So it's really unclear whether the cloud is distorted or not. So we won't know about something like a cloud. This glass of water here is this, this regular example of you put a straw in a glass of water and it looks like it's broken. All right, so there's some discontinuity, and it also shows you not just that, but also you're actually seeing the straw twice. You're seeing the straw off of this surface and off of this surface. Some distortion here. And I also like to show this picture because here, the light doesn't have to go through or between different materials or bounce off of something in order to cause some distortion. So just like the different layers and conditions in the air are causing those distortion, just like observation in the atmosphere. So this is what a galaxy would look like when it passes through a very massive object in space. So this whole thing is one distorted galaxy. And sometimes with gravitational lenses, kind of like with regular optics, we might see objects multiply. We see multiple images of the same thing. So here in this famous Matisse painting, you're seeing multiple images of those fish. Here you're seeing that fish, the same fish off of different sides of the aquarium. So one time bouncing off of this side, one time bouncing off of that side. And again, it doesn't have to go through in between surfaces in order for it to look double. So this is just light bouncing off of different layers of air. This is what it would look like with, still on, right? With a quasar that is being gravitationally lensed by a foreground galaxy. So this is the galaxy over here. And these are two images of the same background quasar. One of them going around the galaxy this way, and one of them is going around the galaxy that way. And now you're seeing both of them behind the galaxy separated, but it's the same quasar. It's two images of the same thing. Nature just does that, like it did that with that glass of water and the straw. You can also have four images of the same thing, 1, 2, 3, 4 in this case. And that happens when some symmetry is broken and it's not exactly symmetrical like that. The position matters, but it doesn't always have to be 2 or 4. It could be 6 or 7 or more than that. And here are some examples of galaxies lensing other galaxies. So what we saw earlier was a quasar. So that's an active galactic nucleus that's extremely bright, throws out a lot of light in preferential direction and looks like a star. So it's called a quasar, quasi-star. So it looks like a point source. And a point source would be lensed like a point source. But if you are lensing a galaxy that has some finite size, it will be stretched into an arc. So those blue arcs that you're seeing here, those are caused by the background galaxy. And sometimes if the symmetry is just right, So the light from the galaxy would not just go from this direction and from this direction, it will go from all directions and form a uniform ring. And that's called an Einstein ring. So something like this. Lots of different geometries. I can look at those things like for days. So this is one galaxy being a lens to lens another galaxy in the background. When a cluster of galaxies is being the lens, then things get a little even more complicated. A cluster of galaxies contains galaxies, but also a lot of hot gas and a lot of dark matter. There's actually 10 times more dark matter, more than anything else in there. The visible light that we're seeing is just a tiny fraction of the whole mass of the cluster. And being so massive, it is causing a very big dent in space-time and causing a lot of distortion. So light from the background source goes around in different, follows different allowed paths. And we will see the background galaxy, multiple images of it, distorted images of it. And the cluster itself would kind of look like a kaleidoscope. I don't know if you can see this, but you can probably see some of those really long stretched thin arcs like here and here and here and here. They're kind of arranging themselves in grand circles around that cluster. Maybe squint a little bit, you'll be able to see it. I'll show you lots of examples. There's arcs stretching around these galaxies over here and this one. And there's lots of tiny little specks, very small galaxies as well. So here's an example of, and is this working okay still? People at home can still hear me? Okay. Right, so here's an example. This is from one of the clusters that I was studying back in 2005. Right, so you have the cluster here causing a dent in space-time. Light from the background quasar goes around this cluster actually 5 times. So it has 1, 2, 3, 4 images and a 5th image that's a little harder to see over here. And those are exact identical images of the same quasar. So if you take a spectrum of it, they look exactly the same. They have the same finger, like spectroscopic fingerprints. And there's other lensed galaxies you can see here. This one is a copy of this one and a copy of this one. And these two here are a copy of these two here. So kind of like, yeah, you're seeing double. How are you seeing that? Yes, you are. This is a little bit more obvious, right? You can see those arcs forming around the center of the cluster. And here are, can someone try to think how many times you see the same background galaxy here? Try to count them. What? 16. All right, let's see. 1 here, 2, 3, 4, 5 here, 6. All those blue galaxies are all images of the same thing. The yellow galaxies, those are part of the foreground cluster. Those are part of the lens. And when we look at galaxy clusters, a lot of the galaxies in them are, we call them red and dead. They're not star forming. There's not like those beautiful blue galaxies. Their star formation is mostly quenched or seized, and they kind of, are still there, but that's what gives them all a very uniform-ish color. So usually in those pictures that I'll show you, those yellow blobs, those would be cluster member galaxies. Here's another example. Can someone spot the multiple lensed galaxy? Maybe people at home.
Yep, we see it.
All right, you see it. All right, here. So we're seeing one here. That's a clue. You see another one? The top one, right? Right here. Another one here in the center. So there are 3 of the same galaxy. And here's again the example that I showed you a few slides ago. So this is what we call a giant arc. It stretches an arc, it's giant, it's very relatively bright. If I remember correctly, that's the first observation. Not this one, this is Hubble, that's for much later, but I think that was the first cluster that was kind of showing Einstein. Yes, you see, we can see it. All right, so what do I do with this how do I use this to figure out how the universe works? First of all, it's a beautiful puzzle. I really enjoy working on this, but we can really learn a lot. And for this lecture, so there's a lot of applications for this, for gravitational lensing. And sometimes I like to think of myself as an instrumentalist. So instead of working with instruments in the lab, this is my instrument out in space. And my job is to figure out how this instrument works. So someone shows me a telescope, and my job is to figure out what the specs of the telescope are without being able to actually go there and mess with it just by the observations. So I need to figure out what the magnification is. I need to figure out what the distortion is, and I need to figure out how to correct the distortion in order to get a nice, clear picture of the thing that the universe is trying to magnify for us. So this is kind of like doing an eye exam by asking you, well, do you see this? Do you see this? But not really. So what I usually start with is I take this pretty picture, usually from Hubble Space Telescope, and I try to identify what matches with what and where those multiple images are and what the distortion looks like, and try to understand what the lensing distortion and configuration is. And then the next thing, I need to come up with a mass distribution that describes the foreground lens, so describes the galaxy cluster that sits there, most of which is dark matter, so we can't see it. We can infer some things about it, like from the rotation of galaxies in that cluster, we can figure out how much of it there is, but I really want to know how it's distributed in space. And once I am able to solve that, I can reconstruct what the actual image looked like before it got distorted by this foreground gravitational lens. It's a lot of fun, but sometimes it feels like we're doing a lot of this. So looking at some distortion mirror and trying to, what I'm trying to do is go from this back to this. So if I have this distorted image of some galaxy, I understand that there's some symmetry around here, some symmetry around here. Try to figure out what the curvature of this mirror is so that I can correct it back and give you the undistorted image back. So here's an example from one of my studies. This is a very giant galaxy, so a very giant arc distorted, and this is the source reconstruction of that galaxy. This is what it would look like if we could point a telescope that's 100 times bigger than Hubble at this galaxy without some distortion in the middle. So this is the one equation that I told you that I'll show. This is called the lens equation, and it connects between the position of the source in the source plane, what we see in the image plane, properties of the lens in between, and some stuff about the geometry of the universe and the distances in this system. So what I do is I try to find multiple images of the same thing. So understand that these are images of the same background quasar. And then I would assume some mass distribution, make some educated guess, compute what the source locations should have been in the source plane. They all should originate from the same source location. And then repeat this until I can find the correct mass distribution that gives me my lensing observables. So as long as these lines don't merge into the same location in the source plane, I'm not done. Once I find a solution that puts all those lines back in the same place, then I have a good description of my telescope. Right. So how do we do it? How do I do it? So first of all, I need to identify multiple images of the same thing. So I want to show you that everybody can do this, and this is really easy. And our brains are actually programmed to do this job. So this is the cloud gate or gate to the clouds in Chicago. I used to live in Chicago. And every time relatives would come to visit, we'd go to Millennium Park and do all the touristy stuff. And one of the touristy stuff is this. And then when you go instead exactly under this shiny thing and look up, this is what you see. There's a lot of distortion, a lot of multiple images. And I looked at this and I was like, oh my God, this is just like a gravitational lens. So let's do an exercise. And this is for you to work with a neighbor. There are multiple images of things of people in here. Let's try to see how many multiple images we can identify of this person with the Macy's bag. Keep going. There's more than one. All right, who wants to tell us what they're identifying? You can come over and point. We're all friends. Show me three of your, oh, you have your own laser partner. All right. Okay.
Obviously, we have the main one.
Right.
This could be, but it doesn't seem like it could be in a likely position, but I do see the point there.
All right, you see a white thing, right?
I see the same thing here.
This kind of looks like pens to me.
Yeah, so I'm not sure of that. And right in the middle, there's several things that could be white bags. There.
So you're just pointing at everything white and saying, maybe that's it. All right, anyone has something more concrete than everything that's white?
From home, John Wallbank says he has 8.
8, all right. I don't know if you can use the annotation thing and show us where they are. All right, you guys had something, right?
On the lower left-hand corner there.
All right, this one.
The shadow, there are 2 right there.
2 right here, right? So this one and then this one. Oh, so there's symmetry along here. So that gives us a clue.
Straight up about 2 feet.
Straight up,
Right there. Isn't that one?
this, I don't know, maybe. That's white. 9 o'clock this. I'm not sure, it is white. And there's one of these in the center. I think it's this one because I see the white and then the black shadowy thing. And it's kind of like pointing in the right direction, right? And then there's probably this thing also. It's very distorted. Okay, how about the person with the red shirt? So this thing, this one, red shirt. I'm starting to understand the symmetry here, right? It's the same symmetry. All right, so let's see, red shirt over here, and then there's this over here, right? So that's very easy symmetry. One of those in the middle. How do we know which one it would be? So red shirt, black, white pants, right? Red shirt, black, white pants, right? And then if there's one here, maybe there's symmetry going in this direction, maybe this thing over here, very distorted, but I see the red shirt and the blue jeans, right? And if I had, you know, that Macy's bag is this, red shirt, Macy's bag, red shirt, right? So we're starting to see the symmetry, and our brain is really, like, our brain knows how to do this because it's people. How about the blue jeans? Which one, right? Everybody's wearing blue jeans. Turns out lots of galaxies behave like people wearing blue jeans, and they're all little blue specks, like those little goldfish, like lots and lots of blue galaxies. But here it is with an actual cluster. So what did we do with a picture with the people? We tried to find some really distinctive colors like red shirts. So we're seeing a galaxy that's very red over here. That's kind of rare. So we're seeing 1, 2, 3 and a fourth one over there. We tried to find things that had some distinctive shape or morphology, like that Macy's bag. So we're trying to look something like, here's a smudge and a dot over here, a smudge and a dot over here, smudge and a dot. It's a little more distorted, but still a smudge and a dot, another smudge and dot over here, following similar symmetry. This would be like the Macy's bag. That's kind of like a face-on galaxy that looks kind of purple. So we have the color, and we have that morphology, and also configuration of galaxies following the same symmetry. So this was like the group of people, right? We had like the red shirt, dark shirt, and white pants, all standing in one group. This is the same group. If I only had this blue jeans over here, try to compare this to any of those other blue jeans, they look exactly the same. But if I have this whole group, then now, knowing that they have the same symmetry, now it all makes sense, and I can map them to each other. So this is the puzzle part that I really, really like, I really enjoy. And I use some software, and I use the knowledge that I have of gravitational lensing to try to help me have an educated guess of where the next image should appear. So then once I identify all those different images of the same background source, I need to find a mass distribution that would put all those simultaneously at their respective points. So all those lines need to come together. So let's say this is just kind of arbitrarily, I select them. So all these need to merge in the same place with the same foreground mass distribution. These also need to agree on where their source should be. These should also agree on where their source should be. And once I have all this solved simultaneously, then I have a good distribution of the foreground mass that would give me back the exact lensing configuration that I started with. And once I have that, once I solved the optics of my gravitational telescope, now I can undistort your galaxy for you so that you know what it does look like with the magnification, but without the distortion. So going back from this to something like that. Right, so we understand how to put a lens between us and the rest of the universe. Let's see what we can do with something like this. First of all, the combination of the Hubble Space Telescope and gravitational lensing is just mind-blowing. It's awesome, and I can't wait to see what the next generation of telescopes is going to do with gravitational lensing. But already it's awesome, and it's already pushing this limit sort of to where we expect JWST to be. Because we're adding this magnification, both in resolution power and an amount of photons that we're getting into our detectors. But admittedly, only in very specific sight lines, because I can't move my gravitational telescope around. I can only look at stuff that's fortunate enough to sit exactly behind a massive object. All right, so here's an example. This is one of the famous ones. The smiley face, the Cheshire cat. I've seen so many names for it. Every once in a while, the media picks up on it again. It's really cute. And by now, you already know what you're looking at, right? This is a foreground cluster. All those yellow galaxies, they're in the foreground. And those blue arcs, those are background galaxies that have been distorted, stretched, magnified by this foreground lens. So this I did just for fun, kind of trying to figure out. I didn't actually do a lot of work on this object. It's just like so famous, and I wanted to know what's going on there, right? To solve back this distortion and understand what the galaxy actually looks like. So starting from this, first of all, I solved what the lens mass distribution was. I don't have that here, unfortunately. And then I took this galaxy over here, this long, elongated, stretchy thing, and I tried to ask, what would that look like without the distortion? And this is what it looks like without the distortion, kind of like a bright core and arms And I even found a galaxy that sort of looks like it. You're seeing the core here, spiral arms over here, kind of like this one. Almost even a fuzz of a, possibly maybe a third-ish arm, not sure. So there's something sticking out in this direction, something sticking out in this direction. I don't know. It's just fun. I didn't publish this or anything. It just, this is what it looks like. It did come out of one of the, I did publish this cluster, but did not focus on this background galaxy. So that's the type of things that I do. So a lot of my colleagues really, really care about those background galaxies. And they ask me, what's the magnification? What's the distance between this bit and this bit in the source plane? So that's my job to solve it for them. I showed you this cluster before. This is one that I really enjoyed working on in 2012. And this is a giant arc over here. It's actually 3 images of the same background galaxy, or partial images. And I took the liberty of putting some coordinates for some of those objects if you guys want to try and maybe look at them. This one is really big on the sky. It's 38 arc seconds. And it possibly could be maybe, I don't know. I'm not an expert. I don't know. You can try. There are others that I know people have been able to observe with backyard telescopes. So this is what the source reconstruction looks like. Again, it's 3 images of the same thing, one here, and one here. You can almost see how those bits map to each other over here. And this is what the reconstruction looks like from the different images. So this is the 4th image that's less distorted. It's also less magnified, but those blobs are the same as those blobs. And with my computer just died. Does anyone have a power cord?
I have one, but I'm a little too far away from you all.
It's just an apple. Oh, here we go. Let's see if that works. Yeah. If it's working, it's just a little broken over here. Let's see.
Never mind. Start.
You're just gonna have to invite me back.
That's right. Whatever it takes.
It didn't, no, it just kind of crashed. I can mime, but all my pretty pictures. Do you want to do a break and do some of your business, and then I will continue?
Yeah.
All right, let's do that. I don't know if
You
this.
got it on your hard drive, not on a memory stick.
Yeah. Memory stick. Who does memory sticks anymore?
Yeah.
All right.
Although it would have been handy right now. Yeah.
All right. I will move on to my office. It will take me 10 minutes, and I'll bring the power cord.
Okay.
And you can do your thing.
Convenient you work at the astronomy department.
What?
Convenient that you work at the astronomy department.
Yeah.
not far
This,
away.
I don't know. This looks like this.
That's
looks
an
a
old
little-
one.
This
Yeah,
looks
for
a
real
little
old one.
iffy.
Yeah.
All right. Okay. To be continued soon.
We got any elevator music?
Yeah.
I just need to remember to bring my card. I'll be right back. I'm so
Okay.
sorry about that.
That's what
Keys.
Oops, something came on.
Oh, wait.
Oh. Ooh.
No, I see the battery.
Okay.
It does say low battery.
However, maybe that charger will.
Yeah,
Okay,
maybe it
let's
was.
try.
Put it back in.
Hendrix version, that's all.
Did ping.
Here we go.
3%. Looks like it's charging. It's just getting interesting. Pink.
Yeah,
All right, let's, what if we let it charge for a few minutes? Do your thing, and then we'll. I don't think it likes having just 1% battery. We may be running the Zoom and the presentation. Expecting. Pink. I'll come back. How long is your meeting usually?
it's indefinite.
Until you get back.
Yeah, exactly. We're no hurry.
Forever.
And of course, by the time you get back, it'll have enough charge on it to work anyway, you know how that goes.
But I'll get my steps in. All right, I'll see you in a bit.
Okay,
Charlie, I'll make my report really, really quick. Okie Tex was great.
that was quick.
And that's my report.
All right.
I can put it on. Upload it. Was there a question for me on the speaker? I didn't hear it.
No. No, he was just commenting.
Wait, maybe I can.
Yes. Yeah, there's some great images.
Sorry.
There are some great images.
Yeah, it's also very big. It will be fast.
Well, actually, maybe this is an opportunity to do officer reports. If we don't finish, they can't hear me, can they?
We can hear you just fine, Charlie.
Oh, goody.
So I was just thinking, we could go ahead and start doing office reports just to use some time here. Looks like we have Adrian's. And Joy was not able to attend. Do I see Liz? She said she,
Liz was not going to be here today.
okay, she said she might join by Zoom.
Yeah.
But no, okay. And Dave sent an email and basically he was just asking for club members if they have any ideas of speakers for 2022. We do have a few months that are still open. So we're open to any kind of ideas. And if anybody's interested, then we can, if you don't have it, send you the speaker schedule so you can let them know what's open. Or you can just turn them over to us and we'll do that. But we're hoping to fill that out as soon as we can. Amy, who's here with us live.
Nothing to report.
Okay. That was even quicker.
Newsletter looked really good.
Adrian, yes, another great one. So how about our guy with the money, Doug?
Guy with the money, Doug, says, we've got 170 memberships, and like the last time, we're carrying about 12 due to COVID considerations, that kind of thing. I've been collecting money for RASC calendars and handbooks, and last time we did it 2 years ago, we got not a lot, and this year I've got requests and payments for 17 calendars and 22 handbooks. I think that's a function of the prices being reduced quite a bit. So that order is going in quick. If I don't get the check by tomorrow, you're probably going to miss out. If you have PayPal or whatever, Venmo, You can do those in the next 24 hours or so. And the order will be going out. I still don't, yeah. Looks like we might be having live meetings, so just shipping them to Liz and people can pick them up at meetings, however you want to do it. That should work out pretty well. And the last item is our TCF Bank to Huntington Bank is complete. And that went without a hitch at all. In fact, in my opinion, good riddance to TCF. I had a lot of problems with them, and Huntington online tools and the mobile app and all that stuff just works. It just seems to be a lot better. So that's the money's in good hands in a new bank, and that's my report. I don't think I have anything else unless someone asks questions.
All good news, Doug. And I believe 170 is a new record, is it not?
Probably.
Yeah, and it was 169 last month, so I don't remember who we added, but we must have added somebody. Unless I
Yeah.
just add people. I don't think I do, so.
And also, I did think about, Liz did say in the email that she sent earlier to the officers that she just wanted to remind everybody that she currently has the observatory keys. And as Doug had mentioned, the publications will be arriving and she is gonna help with the distribution of those. So with that, somewhere behind me here is Jack.
Yes, can you guys hear me?
Yes, we
Yes.
can.
Okay. Basically, as I reported last month, we did clean up the observatory and the graffiti, repainted the walls and everything. And we're still doing some grounds maintenance around the observatory now, clearing up brush and things like that. And that's been working out. We have done a little work on the observatory, just testing out the electronics because we haven't used it in such a long time. So with that, I'd like to move into part 2. I will make this very quick. And now's probably a good time to do this, but some of you may remember a couple, 2019, our last meeting, we were selling our famous red ruby litho. And some people liked them. You can
We
put
just
them
get a
on
little
your,
further over. I think the camera will get you.
oh, okay, there you go, on the camera.
Yep, we can see it now.
For their cell phones, laptops, cutting them out, pieces for flashlights and that. But wait, there's more. We got a great deal. 2019 price, pre-COVID. $1.
Oh,
That's all. It's cheap.
so
You can't get it sent to your house because they're gonna charge you $1.59 for a cardboard tube to put it in. So $1 a piece for, just give me $1. No credit cards, no checks. Okay, yes. George is still appreciated. It's okay. Oh, another George, okay. Well, here. Let me give you these with
mhm.
you can't buy these. for this
On a
purpose.
rubber band for it. This is
Just
just
to
too
hold it, yeah, to keep it in
Thank you.
place. We don't. Okay.
I can make all the galaxies red.
Okay. Any more? Oh, okay, cool. Cool.
Anybody on Zoom
Oh, gee.
is interested, we'll try to download one to you.
Well, I don't know, maybe I can get Captain Kirk to be, Scott is still available, I don't know.
I don't think Scotty's available anymore.
Really? Well, sorry about that then. Good. 2 and 2. And of course, I'll be sending Doug Scoble a check in the mail for $4, I think, so far. Guess we could see that.
Quick question for you, Doug. When you get funds in from PayPal, do you just transfer them directly to the bank or do you leave them sitting in the PayPal? That's your own PayPal account. So you transfer those to the bank, right?
Yeah, I transfer it to our bank account.
Okay, yeah, over
Same thing
over
with,
in,
yeah, same thing with Venmo.
yeah,
So,
yeah,
and
over
checks
in,
are just used, yeah.
over in the was, it's the was's PayPal account, so it just sits there when people pay us using
Oh,
PayPal. So I've got like 3 different sources I have to look at. So a little
yeah,
harder, but
I just use my own personal accounts and transfer it over. And I have our Lowbrow bank account linked to my PayPal or my Venmo, so I have to make sure it goes to the right account when I transfer it out.
yeah,
I haven't made that mistake yet, but
Nope.
can't promise.
well, no, that you've been on top of it for so long. We don't suspect you're about to go buy a Skymaster now. So I think we're in good hands.
You would still have the.
How do you know if you've been to his house?
I haven't been to the new house, and I saw a lot of telescopes being sold off. So
Well, I do have a bit of news if anyone cares to listen. Some of you may know that up here in Sutton's Bay, which is, you go along the west arm of Grand Traverse Bay to the north, about 15 miles from Traverse City, there's a little store called Enerdine. Well, Enerdine happens to be the largest telescope and eyepiece and accessory dealer pretty much in the Midwest.
Yep.
And I am working there part-time.
we talked to the Camp Lowbrowers talked about that. We found you told like Nate Murphy or something, and we all plan to come and visit you at the shop at some point.
Looking for that employee discount.
Yeah.
Yes.
There is-
Discount too.
Well, if you want to work there and after 30 days, then you can get the employee discount too.
That's no problem. It's a 3-hour drive for me. No sweat.
No
I think I
sweat.
can pull
Yeah,
that.
for you, that'd be nothing. For you, that'd be nothing, Adrian.
Very true.
So I'm curious, Doug, how does, what are the COVID regulations or protocols in the shop you're working at?
We all have to wear masks. So we wear masks and we ask that customers come in and wear masks, and we provide right in the front, there's a sign and there's masks. If people don't have their own, and they can use one of theirs. And 95% of the people say, oh, no big deal. Most people have them with them. And then there's a small handful that say, okay, I'll just leave. And a lot of those people are just people that they're not there to buy anything. They're just walking around Sutton's Bay because it's a tourist town, right? And so they just stick their nose in, and because most places up here, very few places require masks. That's one of the few that I know of. So it's been pretty open up here for a long time. But most people comply and don't complain. And I don't complain. I have to wear it when I'm in there, at least when there's customers in the store. When the customers leave, and there's times when there's nobody in there except for us, and we pull our masks down, but we put them back up if someone walks in.
Yeah.
It sounds like you've got a handle on it there.
Oh, yeah. Yeah, the guy that owns it, well, actually, he doesn't own it anymore. It's his wife, technically, that owns it. He taught at the university there in Traverse City, Northwest Michigan University or college. I don't know if it's college or university, it doesn't matter. He taught there astronomy, and I forget what his other discipline was. He taught there for like 40 years. I'm the youngest guy there, believe it or not, other than a couple of students that they hired part-time. So
How's
Yeah.
it feel to be new blood again?
yeah, I'm the young kid on the block. So it's interesting. It's totally out of my box. You know, I sat in front of a computer for 40 years doing software engineering, and working retail. It's a totally different thing. So got to keep busy. You got to look like you're busy. Learning how to run the cash, the point of sale thing, which is pretty easy, really. But they've got a lot of cool stuff in there. A lot of cool stuff.
Can you
Well,
afford
congrats.
it?
What's that?
Can you
Can you
afford
afford
any of it?
A lot of it, no. They have a really good selection of binoculars too, and they've got Swarovski. If you know anything about Swarovski binoculars,
great.
they're like second to none, as far as I know. And if you look through them, it's like you're not looking through anything. They're just, it's like things are just closer, and they're pretty expensive.
Yeah, they are.
I did buy 2 items today. A map of Northwest region of Michigan and the Upper Peninsula of Michigan. So I spent what, $11 or something.
Is that with or without the employee discount?
Yeah, I haven't been there long enough for the employee
Oh,
discount.
gee.
Yeah, so anyway, yeah, so it's fun so far. A lot to learn.
Sweet.
Okay, so with that, we'll continue. We've got 2 more officers to report, actually 3 if you include me. However, we are ready for part 2.
I'm ready whenever you are. Don't stop.
Okay, okay, let's go ahead and finish officer report quick. Then we'll get to part 2. So that would bring up Jeff.
So far tonight, we've got 22 in person and 22 online, 10 in person. That's pretty much all for right now. As far as the GALAX things, we had a successful AATB, the Astronomy at the Beach. On Friday, we had about 673 people viewing, and on Saturday, about 478. Those are views, so they're not necessarily differing people, but it was our best thing. In the minutes, I got a breakdown of the various events there, but that's what the totals were. Importantly, the nominations are now open for the 2022 officers, and they'll be open until the January 13th election meeting. So we're encouraging all of the member clubs, of which the Lowbrows is part, to, if there's anybody you think is doing a great job representing Lowbrows up at GALAX and kind of filling roles, then nominate them. And you can send that to, well, me or any, I think we have a GALAX.io group list there, a groups.io GALAX list. But any of the officers can get your stuff up to those people.
My name's Adrian Bradley, and I approve of this message. Also, tell them the dates. We did select dates.
Oh, what's the names?
Yep, that's kind of important too.
So it's on my list, coming. The election will be January 13th. And that's the second Thursday of the month is our meeting day. November, we won't be having a meeting. And we have set a tentative date for the 2022 Astronomy at the Beach. It will be September 16 and 17. These hopefully will not, currently they're not interfering with the Great Lakes Stargaze or Okie-Tex. So, and they should be astronomically decent, if not pretty reasonable.
Harvest moon is on September 10th, so we are avoiding the waxing moon. We will get some waning moon setting during that time.
And just as an overview for Astronomy at the Beach this year, we basically came to kind of consensus that due to our changing COVID conditions, it was really difficult this year to do a decision on whether to do in person or virtual. And that kind of had an impact on how effective all the communications and marketing were. But we were still pretty pleased with the numbers, all things considered. So I think that's everything that I had in my notes to talk about.
And I have nothing further to add.
Okay,
I get it about right, John?
That's good. We need participants. We need people who want to serve as officers. We need people who want to serve on the planning committee. If you want to get involved in helping to plan for Astronomy at the Beach, you are very much welcome. We have some really good, highly qualified people in the club. We'd love to welcome you aboard.
Well, I guess there's one other thing I can add, is that's the shout out to the officers. Similar to last year, we had Bob Tremblay, who did Webb's the Webb work, John Wallbank, VP. Jeff did a whole bunch of footwork for us. We had Brian Ottom, as usual, getting communications out. We were a little late in having him spread things, but he did. It turns out his event drew the most people, even though we were able to get a contact from the Southern Hemisphere to share some Southern Hemisphere skies over Zoom. So that was a nice change to how astronomy at the beach went, but we still, overall, we had Doug Bach as well, did a presentation. Auni did a great H Alpha presentation and got a lot of views. The Ford Astronomy Club came through with a number of programs on their channel. I can't think of anyone else. I think that was basically it for presentations this year. And they all seem to go pretty well. And I know I'm probably missing someone else. Bridget Harwood is our connection to Island Lake. And even though we haven't been able to do anything at Island Lake Recreational Area for a couple of years, she's still on board with us and looks forward to hopefully maybe next year working with us directly. We still have to make sure that we're doing right by our member clubs and we're not overstepping the recommendations as far as handling COVID. We saw a few clubs, including Nebraska, do some things in person where they mandated masking, social distancing, and shared telescopes using iPhones instead of eyepieces. We've got some things to look at as a group. And so starting next year, we'll just keep our eyes on how the COVID situation is progressing and, try and look at that situation to see, maybe next year we can get back to being in person in some shape or form. But overall, we wish to be safe and we do not wish to put anyone at risk if you do come out to Island Lake Recreation Area. And like Jeff said in his report, and I think John, you did too, the risk was just a little too great and we erred on the side of caution, just like we did last year. So that's, I guess, President's remarks. And again, the board did a really good job of navigating the tough waters again this year with COVID. I take no credit for it. I give all the credit to John and Jeff. So there. And any other questions you can ask any of the officers that are a part of GLAC. Any questions or comments that you have. And
Okay.
great report, Jeff.
Thank you.
Yes, thank you. I just have a couple quick things. Just to announce that we have returned to in-person meetings, as you can see, in hybrid fashion. And it appears that it's going to work for us. So that was good. We're kind of boldly going where no lowbrow has gone before. Also, we got a request for an event at the Westland Library. As you might recall, we've actually made a couple of appearances there and they went very, very well. So it turns out they're going to be contacting me in March to set up something for this spring. And with that, I will go to Krishna.
The website still works, so there's that. The communications committee met, and so there's updates on that Jeff has talked about and will be sending out. The big one from the website perspective is we are exploring trying to move away from our current platform to one that's a little bit more modern and allows people without HTML and coding skills to make edits and to update the content a little bit more dynamically and easily. So we looked at commercial options for that, and they're often just too expensive or just locks you into that system, so you can't really move it and get out of that easily. But WordPress is a very popular system for doing this, and U of M actually supports it now. So we're exploring moving our website over to the WordPress instance at U of M. But that's going to be a long project, not something that's going to be quick. So we're starting by using my lab's website as a guinea pig. So I ported my lab website over to that, and I'm playing around with the tools a little bit. They seem to be very tractable and easy to use. So once I figure out how to do things on something that's frankly low stakes because no one cares about my lab website, then we'll move it over to our Lowbrow website.
Report. Okay, thank you, Krishna. So with that, we can return to gravitational lensing part 2. Putting up with this, Karen.
Oh, no, thanks for not being mad at my technological issues. I'm off Zoom probably, right?
Yeah.
So I should
Yep,
log back
think
in
so.
so you can see my slides.
Oh, yes.
Do people need another break, like a couple of
No,
minutes?
we're good.
We're good.
We shall plow ahead. Like the snow that's probably coming in a month.
All right, so I'm on. And we'll start exactly where we left off. And share the screen. How's that?
Perfect.
Mic up again.
Okay, is this working?
Yep, we can hear you.
Okay, so we were here and I showed you how I reconstructed the source plane image of this very highly magnified stretched galaxy. And we were, I think exactly where my computer crashed is where I told you how, or showed you how the resolution that we're getting with the gravitational lensing, distortion and magnification really allows us to resolve very small structures in this very far away galaxy. So this image has a magnification of about 3, factor of 3. So it's 3 times more like brighter and more magnified than its source. And this is something like 17. So you can see those little blobs that I here just look like a smudge pixel. Here are resolved, and we can actually measure their sizes, and we can measure how big is a star forming region at a faraway galaxy, where we can start asking questions like how does this physical condition change along this galaxy bit by bit, clump by clump, and see how it built up over time. And even how is it rotating, or how is it, this one's probably interacting. It could be even 2 galaxies, one here, another here. They're interacting with each other. So that's super cool. Here's another one. This one you would have been able probably to resolve, but it's too far in the south. So you'll be looking through the earth to see it from your backyard. Maybe your friends in the Southern Hemisphere would be able to view that. That is dubbed the sunburst arc. And this actually has 12 images of the same thing. So there's 6 over here, another 3, 1, 2, 3, 4 here. So that's 10, 11, and 12 is over here. So this is just a zoom in on the one with the 6 images. So there's 1, 2, 3, 4, 5, 6. All those reddish blobs are all images of the same thing. And all those little clumps over here. So you can even see the symmetry between these clumps and these clumps. Kind of they're symmetrically. Someone at home needs to mute. So for this one, this was one that we're actually studying the heck out of. And we're going to point James Webb at it as well next year. So this is actually out of our James Webb proposal, the JWST proposal. We're going to look at this galaxy and understand what it's made of, even better than what we did with HST. And the source reconstruction, or what does the image of the galaxy looks like before it was distorted, looks something like this over here with those many, many little clumps that you're seeing here. This is all kind of star forming regions of this galaxy is generating stars. And this is the type of galaxies that create most of the stars that the universe is made of right now. It's right there where the universe made most of its stars. And also another thing that's interesting about this galaxy is that it's leaking Lyman continuum emission. And this is the type of radiation that we believe ionized the universe when it was really, really young. So the universe was initially ionized, and now like light is traveling from that very early on time to here. But this galaxy is in a location where we can actually see this in action. So we're trying to study from this galaxy what very high redshift, very far away galaxies might look like, and what the mechanisms are that allow those galaxies to leak this very particular kind of radiation. So here, this is a reconstruction of this galaxy in UV continuum, Lyman alpha and H beta. So kind of like if you use those filters on your telescope, this is what it would look like compared, but redshifted to different wavelengths, so this is far away, compared to a local galaxy. Kind of looks similar. It has those star formation blobs and radiation emitted and all that. So this is something we're extremely excited about. Sunburst arc. Here's another, this is not my work. This is by one of my colleagues. Dan Coe discovered one of those very far away galaxies with this tiny little red speck that you're seeing in 3 locations around the cluster. This is at redshift 11, 13.3 billion light years away, really when the universe was extremely, extremely young. So this is the kind of things that we're, not just what I was showing you before, looking at something at very great detail where it's more nearby, but really trying to identify those very far away galaxies, trying to peer into the universe like James Webb Space Telescope would do, but before having that available to us. Here's the other lensed quasar. So if you write down this, this is, so one of my good friend and colleague, Håkon Dale at Oslo, he's also an astrophotographer and an astrophysicist. But he's tapped into those communities of people trying to observe things and post them online. So he pointed me, I asked him which of the arcs that I'm going to show, which lenses could be possibly observable by people from their backyard. So this might be one of them. If you maybe take a long exposure, you might be able, and this is someone who actually did and saw that through their telescope. This is a close-up view of it. 1, 2, 3. Actually, you can circle them. 5 images of the quasar, more images of some other background galaxy. All those are really helpful and understanding for me to be able to solve that puzzle and have more and more clues in order to understand the overall configuration of the cluster. Here's another one. This also has multiple images of the quasar. This is a different link. Someone else tried to look at that as well. 1, 2, 3, 4, 5, 6 images of a background quasar, a giant arc over here, some more lensed galaxies over here. And so this is a picture from the Hubble Space Telescope. And one of the things that's interesting about observing lensed quasars or anything that has intrinsic variability is that we can tap into that information as well. So one thing that I didn't tell you earlier when I described gravitational lensing is that when light goes along different paths, it also takes different amount of time to get there. So kind of like if you use Google Maps to get from this direction or from that direction, it will take you not the exact same amount of time. So light does the same thing when it travels through the universe. We call this a time delay because there would be a lag between the 2 different paths. So if the light starts from this background galaxy, goes along different paths, we'll see that light coming at different times. For most things in the universe, we won't be noticing any difference because any changes on a galaxy, on the time scales of changes of galaxies are extremely long, much, much longer than our observations. But there are objects that very, very rapidly. So supernova explosion is one of them, or variable quasars is another one. And we can tap into this information for multiple things, but one of them being to understand what the expansion of the universe is, because as this light takes longer to travel from this direction and this direction, the universe expands, and that changes the time lag. But the other, I think the even cooler thing than this is that we can see the future, or we can tell the future with this information. So if I have two images of the same thing, and I know that one image is going to get to me first, and then the other one is going to lag by some time, could be weeks, could be months, it could be years, from what so I think this one was first, from what this one was doing, or what this one is doing right now, I can predict what the other images are going to do in a few months. So if, let's say, you really care about quasars and you really want to study this quasar when it flares up and when it throws up a lot of radiation, you can follow up this guy, this one here, and know when it's going to get brighter. And then you know that with a lag of, this one has a two-year lag, you point your telescope at it exactly when it flares again. And now you can really tell the future. You can tell when your astronomical objects are going to do something where it's otherwise impossible to do. I think it's super cool. Yeah, very rare too. Here's another one. This one, the other one was also something that I was involved in, and this one was super cool. So one of the things that didn't say in my lovely introduction is that for my PhD, I was a supernova hunter. I looked for supernovae in HST data, and I found a bunch. And then I discovered gravitational lensing, and I was like, whoa, this is what I really want to do. This is my passion. This totally fell in love with this, curved universe and distortion and solving that puzzle. But then I knew that someday it might happen that those two worlds will collide, and I'll see a supernova that is also gravitationally lensed. It's just a matter of time until it happens. And this is it. This is the same cluster that I showed you a while ago, and I asked you to find those three kind of spider-looking galaxies over here, 1, 2, 3. And this one is a cluster that the Hubble Space Telescope also stared at for a very long time. It was one of the deep fields. It's called the Frontier Field Project. And as the telescope was staring at this cluster for a very long time, a supernova popped right here around this galaxy. And it actually appears 4 times around this lens. So 1, 2, 3, 4. It looks yellow because when they observed it, they were using a different filter. So it doesn't necessarily have to be a yellow supernova. And this happened because the spiral arm here is kind of wound around this galaxy. So it's lensed by the whole cluster, but then it's lensed again by this one foreground galaxy. And this was absolutely mind-blowing. And me and a bunch of other people tried to understand what's going on and we'll very quickly refine our models and try to figure out what's going on, and also predict where another image of this thing should appear or has appeared in the past. Maybe we missed it because this galaxy appears here and also here. So this supernova that we're seeing over here, the light from the supernova left a long time ago, and it should also reach these other 2 positions. The question was, when is this going to happen? And can we actually figure that out? So we did. We actually did figure it out. We figured out, first of all, where that supernova should happen. So in this galaxy, it should sit right on this spiral arm over here, and in this galaxy, right on this spiral arm over here. And all of our models said that in this galaxy happened first. So that the light would have reached us, I know, like 15 years ago. So we missed that. Then this one and this one last. And we predicted that it would appear around a year after this one. So this one was, I remember where it's like, oh, November, December of the year after. And turns out that we were right. most of our models actually predicted correctly the appearance of this supernova right here. So this is the before and this is the after. There's nothing there. And then there's tiny little speck here. That's the first observation where they got that supernova to actually show. So this is, as far as I know, the one and only prediction of a supernova explosion observation ever. And we were only able to do this because nature provided us with this wonderful cosmic telescope that bends and distorts space-time and all that. The last thing that I want to show you, that's my last slide, also kind of famous. I don't know if you've ever seen this. This is called the bullet cluster. And probably one of the most important tools the gravitational lensing has. And I haven't talked about this at all today because I focused on it being a telescope to look at the background universe because we all like telescopes. But when I solve for the mass distribution of the cluster, I'm solving the mass distribution of the cluster. I map where the dark matter is with gravitational lensing, where you would otherwise not see it. And gravitational lensing doesn't care about what type of mass this is, luminous mass, dark matter, gas, galaxies, anything. It all has mass, so it all bends space-time. So gravitational lensing allows us to know exactly where the total mass is. And in this cluster, there's two components. There's one cluster component here, another cluster component here, and at some time in the past, they went through each other like a bullet through an apple or something like that. And the dark matter distribution or the gravitational lensing finds the total mass located here and located here. The pink stuff that you're seeing in the center, that is hot gas, and that's observed with the Chandra X-ray telescope. And clusters have, by mass, a lot more hot gas than luminous galaxies. So about 10 times more hot gas than stars and galaxies and so on. And when these two clumps of cluster pass through each other, the galaxies pretty much pass through and through. Their cross-section for interaction is very small. They hardly collide with each other. It's kind of like, it's very sparsely distributed, and they feel some gravity, but they won't collide. Dark matter behaves the same way. It's non-collisional. So it generally goes where the galaxies are going. And gas does not. Gas is collisional. When you throw a clump of gas on another clump of gas, there's shocks, there's compression, it heats up, it interacts with itself. And this is what we're seeing here. We're seeing the shock, the bow shock here of the pink stuff, that's the gas, and it's displaced where all the other mass is, which tells us that most of the mass in this cluster is not in the gas. So if the gas accounted for all the mass in the cluster, then we would see the gravitational lensing around this clump over here. But instead, we're seeing it where the galaxies are. And this is one of the strongest evidence that dark matter exists, and that it's not that we just don't understand gravity in a way. Because if dark matter did not exist, then most of the luminous mass in this cluster would be this gas clump. There's a ton of gas there. But instead, the fact that we're seeing it at separate clumps where the galaxies are tells us that there's dark matter, but also it tells us that one of the important properties of dark matter is that it's non-collisional. It behaves like galaxies and stars, and it doesn't behave like gas. It doesn't encounter itself and create shocks and things like that. So this is a story of the bullet cluster and how it relates to gravitational lensing. And the way that it relates to lensing is that the lensing enabled us to identify where the total mass is and separate those different components from each other. That was my last slide. I would be more than happy to take questions about any of this or anything else. But thank you for your time and patience. Can't see me smile.
Radio structure. clouds?
No, we use, so I'm not familiar with those techniques, but we use something a lot more straightforward. It's kind of like forward modeling. So you assume that the mass, so there's different ways of doing this. In all of them, you assume that there's some mass distribution, and then you iterate on that in order to refine it and find the mass distribution that solves the lensing configuration. So the tools that I use assumes that the mass is distributed as like big blobs of dark matter with some known distribution. Like it drops with some slope. It has parameters like ellipticity, where it's positioned, where it's oriented in space, how steeply the mass falls down as a function of radius, and so on. And those parameters, the software would iterate over those parameters and try to change them in different ways using Markov chain, Monte Carlo usually, and kind of like explore the entire parameter space until you find the best solution. There are other ways of doing this. Some other ways would just randomly place mass everywhere and iterate on those clumps of mass. And
Sort of a comment and a question. The comment is, I think it's really cool to actually pay it all. And my question is, how many gravitational lenses have we discovered so far?
ooh, how many gravitational lenses have we discovered so far? A lot. So I'll just pull away from this slide. I don't have a number. I don't have an actual number for you. There are now a lot of new. So it's in the hundreds and or thousands, I believe. Just to throw a number out there. There are more little ones than big ones. So a galaxy that's lensing another galaxy, rather than a cluster of galaxies that's lensing, just because there are more galaxies. And now there are, with the new surveys that are observing large chunks of the sky, and the emergence of technologies like machine learning, as well as like a galaxy zoo and things like that. Teams are discovering more and more and more and more galaxies all the time. And just thinking of the ones that I have on my computer is about 200 right now. And it keeps growing. It used to be that I knew every one of those by name.
So you're getting a new telescope on a regular basis.
Exactly, yeah. Sometimes it's frustrating because not always I can't always solve the puzzle. So sometimes I have this shiny telescope and it's like this bright magnified galaxy behind it. It's like, I don't know. I can't figure it out. I don't know what the magnification is.
The number? Number of imaging?
The number, the question is, can the number of lenses tell us anything?
If you have a lens, you have both a foreground galaxy and a background.
Right.
So you could, if you have a foreground galaxy.
Yes. So the question is, can we say anything? Can we learn anything from the number of observed gravitational lenses compared to the number that we can calculate? How many of those should be? Absolutely. And that's a field that's called the arc statistics or lensing statistics, where if you can simulate the universe in a computer and ask the question, how many clusters are there, or how many galaxies are there that can form? Not every galaxy or every cluster can be a lens. They need to be up above some threshold of mass. And then you can ask the question, how many do we expect to find? Compare that to how many you actually find. You need to very carefully fold in all your detection detection functions, or, if I found 100, does it mean how many, are all these 100 real? Or maybe there are 300 and they just missed 2/3 of them. So we need to fold into those calculations all of our selection functions and so on. But then, yes, you can, if you compare your prediction to your observation, then that can tell you something about what went into your prediction. And probably 10, 20 years ago, that was, there were ways to, that was one of the ways that people try to decipher whether the epoch when clusters of galaxies have started forming, do we understand that correctly? What was the typical density that clusters of galaxies were forming with? It could tell you, it has in it, encoded in it, information about the acceleration of the universe. Is it, was it accelerating earlier or decelerating? Because that would depend, that would change the density of clusters and the density of sources in the background and so on. So yeah.
Years ago.
What?
Years.
At least. But it's not, I don't know, yes.
So that famous little snapshot that you alluded to from 1996 on Hubble there with gravitational lensing, then would that little snippet have been affected that what we were actually seeing was not as many galaxies as perhaps we first thought?
So the question was, is gravitational lensing changing what we saw with the Hubble Deep Field? Not with the Hubble Deep, well, I don't think there are any lenses in front of the Hubble Deep Field, definitely not big enough to cause this effect. But when we do have a gravitational lens, something like this or any lens, it magnifies the whole background. So if the picture that I'm seeing from Hubble, the field of view is actually something smaller in the background because everything gets magnified. So if you are in the game of counting galaxies, if you want to say, how many galaxies are of each luminosity, it's called a luminosity function at this redshift, at this distance from us. You have to compensate, if you're behind a cluster, you have to compensate for this magnification of the entire field. So absolutely, yes, this is an effect. Not with the Hubble Deep Field, but if you want to use those, so I said like the Frontier Field is one of those projects where they pointed the Hubble Space Telescope at some clusters, 6 clusters of galaxies, trying to do JWST science before JWST by using this extra magnification. And it was very successful. But all those studies of number of galaxies at the epoch of ionization at redshift 6, 7, 8, 10, they had to take into account that they're looking at not a 2x2 arc minutes, but it's something a lot smaller and distorted. So even if you just wanted to count galaxies in that field, you needed someone like me to tell you what the magnification is and what the actual volume is that you're looking at.
Do we have any questions from our Zoom audience?
Oh, we have more audience.
Questions from the Zoom audience?
Are they hearing you?
I don't think so.
People at home, do you have any questions? There's chat. There's something in the chat.
Oh. Room like
So we can hear you, Dr. Sharon, easily. We're not hearing the conversation in the room anymore like we were earlier.
Oh, okay. I tried to repeat every question that was in
Yeah,
there.
and you did.
Is
That did help.
are there questions from people at home that I can answer?
I don't have any other than the only gravitationally lens thing that I know of that I didn't see a picture of, I think was dubbed Einstein's cross. It was another quasar, I think, that was gravitationally lensed. It's somewhere in Pegasus.
There's
But it's
go ahead.
the same exact thing that you've already gone through in a lot of detail with the presentation.
Yeah, there's lots of them. There's a whole bunch of lensed quasars, part of those thousands of galaxies that are probably lensing other galaxies. Yeah, but they're super useful.
Just I had a question about
Mm-hmm.
you're able to estimate the quantity of dark matter based on these types of measurements, but there's other independent ways to measure dark matter. One that I'm thinking about is going back to the microwave. Just wondering how much agreement there is between those two. I know energy, there's a big disagreement about that.
Yeah, so the question is, dark matter, we can measure it not just with gravitational lensing, but there are other complementary methods for measuring how much dark matter there is. Interestingly, so far there's no big disagreements. All the measurements of anything we're using any methods show that dark matter exists, it's real, it's there. Someday we'll maybe capture a dark matter particle in a box and know exactly what it's made of. But one of the ways that gravitational lensing and other methods are complementary to each other is that they might be able to measure the distribution of dark matter on different radial scales. So some of the other methods for measuring, let's say, a total mass of a cluster, or where the dark matter distribution is in the cluster of galaxies, one of them would be through the velocities of galaxies in the cluster. So the galaxies move around, and we can measure their velocity, the component of velocity that's moving away from us or towards us, just like the Doppler effect. And by measuring that for a whole bunch of galaxies, we can statistically know how fast they are moving around the common center of mass of the whole system. The more massive the cluster is, the higher the velocities are, and the broader the distribution of velocities are. So from there, we can go back to an actual number of how much mass there is, like 10 to the 15 times the solar mass, the mass of our sun. That measures the distribution on a large scale. We can use weak gravitational lensing, which is something that I didn't even talk about. This is the very small statistical distortion of galaxies in the background. They won't be multiply imaged like this. It won't be very strongly distorted, but there will be some small distortion that we can statistically detect and use to measure how much mass there is. That's actually one of the ways that was used for the bullet cluster. That also measures the mass on a large scale. X-ray luminosity, if the cluster is relaxed, or if the X-ray is nicely distributed in the center, not like the bullet cluster, that is also correlated with the amount of mass. The more massive the cluster is, the hotter the gas in it is, and that's correlated with the total mass. And with the cosmic microwave background radiation, the photons from the cosmic microwave background radiation go through the gas in the hot cluster and upscatter their energy, and we can see a little shift in the energy. That's called the Sunyaev-Zeldovich effect. So we can see a little shift in the black body spectrum of the cosmic microwave background radiation, and that correlates, the strength of the signal is correlated with the mass. And that also is measured on a different scale too. So if we combine strong lensing at the very core of the cluster, so right here, then add X-ray, which is kind of like out here, and then add the Sunyaev-Zeldovich effect, which is out here, and the velocity dispersion, which is even farther out, then we can measure the whole mass profile all the way from the core all the way to the outskirts of the cluster. So those methods are very highly complementary to each other. And by using all those methods in combination, we can learn even more things, not just how it's distributed on different scales, but also how it interacts with other clumps of dark matter, other structures, map filaments. There's a lot to do. Oh, another thing which you can do is you can use, so I don't know how much you know about dark matter and the attempts to detect dark matter on Earth and detectors like super colliders or like smashing particles at each other. But if you take two galaxy clusters, like this would not let me go through anymore, like this one. So these are two clusters or a cluster and two subclusters or two big groups. You smash them into each other. That is the universe's strongest super collider. You're just taking a whole bunch of dark matter and smashing it into a whole bunch of other dark matter. And you can use those objects to try to understand something about the dark matter cross-section for self-interaction with itself. Yeah. Someone asked me recently, like if I had a lab, like a lab in my building that I work in the lab. And I was like, the universe is my lab. It has all those things in it. I just need to know where to look. All right. If there are no other questions, thank you very much.
Thank you. And as a humble token of our appreciation, we would like to present Karen with an official Lowbrow t-shirt.
Nice, I love it. Thank you so much.
Thank you. Okay. So we did officer reports. Does anybody have anything else, Zoom or in here, that they need to bring up or would like to bring up? So hearing nothing, do I hear a motion to adjourn?
Motion to adjourn.
Okay, anybody?
Seconded.
All righty,
Third.
okay, thank you. It's not official, though.
Now it's official.
Buddy.
Good night, everyone.